Hey everybody, thanks for coming. I'm Dorian from Imerza, here to talk about data-driven dynamic worlds and large Unreal Engine projects. Imerza, if you'd like to know more about us, we are a global digital twin consultancy, and we really try to partner with visionary placemakers and help them both design and build their project, but really tell the story about them as well. I'm co-founder and CTO, and the range of projects we do is actually pretty broad. Everything from sales applications, design validators, global or countrywide digital twins, and operational digital twins, large real estate development projects, like one of the ones we're going to be talking about today, as well as experiential marketing centers. The project we're talking about today is one of the projects we're working on in Saudi, called Diriyah. For projects like this, you need both a really talented team to put it together, but also a great client. And without that, projects like this just couldn't happen, period. So we're talking about transforming massive BIM models with dynamically data-driven content. So why is this important? Clients really require accuracy, speed, and insight, while at the same time also requiring really high fidelity imagery. And unfortunately, for everyone that works in the field, we all know BIM models are and can get both quite massive and very messy. So we, in order to approach these projects, we really need to design workflows that can both scale and adapt with the project. So when we're talking about massive today, we don't necessarily mean area, which we've done lots of massive in that sense projects as well. But what we're talking about today is really density of information. So we're talking about projects with over 1,000 Revit models. We're talking object counts, excess of 1 million, 1 or 2 million objects. Multiple design teams working on it with tons of different design schemas, and just a ton of complexity in the BIM data. The one we're showing today, technically, it's got just under 3,000 Revit models in it, and is somewhere between 2 and 3 million objects. So this is a quick overview of it. As you can see, it's quite dense with BIM data. All of this running in real time, 4K, over 30 frames a second. Much of it getting streamed in dynamically, which we'll touch on a bit of that in a sec. But the really special thing about it is it's also really high fidelity information. So when we get down to street level, we have high res foliage, we have all the nuts and bolts and every bit of design information in there as well. I'll let this play for a bit. Of course, all the design information, material libraries, foliage libraries, et cetera, all of that is getting specified by the design team and getting generated dynamically based off that data and replaced in Unreal with higher res assets. So I'm going to touch on 3 major topics today. First one being BIM optimization and processing. The second one, connecting to the data, and then manipulating the models based off that data. So some general best practices for optimizing the BIM is, first and foremost, plan for your use cases. That's the number one critical thing. If you don't have a plan in place, you don't know what you're going to be doing on the other end, it's never going to work out. We collaborated really closely with the client to define all of this information, and then things went quite swimmingly. Another really good point is to merge as much of your geometry as you can based on those use cases you've defined. So whether it's level, discipline, class, material, try and merge geometry to condense some of it, and strip any unnecessary elements. So if you know your use case, say I'm just making stuff up, say you're not going inside, you can strip out all the furniture in a BIM model, things like that. And depending on how you're processing things, you definitely want to preserve your metadata in an external database. So Unreal meets bad BIM. Yeah, so one of obviously BIM has been around for a while now. It's well used in the industry, but unfortunately, BIM data is never totally perfect. It's never totally correct. So when that's coming into Unreal, you have to plan for all those different edge cases. And best practices: check early, check often, see what pitfalls you might be coming up against in the future. So we have a validator that processes all the BIM models, lets us know there's X number of objects without materials, there's X number of things that don't have layers assigned, et cetera, and gives us some insight so we can then address it however we see fit. So in order to do this, we needed to extend the Datasmith exporter. So if anyone's worked with the code in Datasmith, there's a lot of to-dos there, and Datasmith likes to make a lot of assumptions about things that we don't necessarily agree with. So being able to define that and then define that on our own means it won't be a battle from the ground up in the future. And Epic being so kind with the code open source means that whatever we don't like, we can just change. So this is just a quick example here, bringing a Navisworks model, a collection of Revit models. We're dealing with all the level mismatches, all the splits between things, and we can optimize that file literally down to 98, almost 98% size of what it originally was. So some of the things we're dealing with and are caught in that early validation phase is inconsistent level, layer, base constraints, sloppy material applications, no material applications. Sometimes you'll have a Navisworks file that's a collection of maybe 10 Revit models, but then there's a SketchUp model in there too. And those aren't actually BIM objects. So you have little or no metadata. And they also then tend to have a lot of detail in them that you have to deal with. So one of the other major things is things not instancing correctly. And a lot of if the CAD operators aren't putting the effort in to maintain objects, then they just won't look great when they come into the engine, and that validation stage catches all that. So our general pipeline, we have a connector to ACC that we're then doing two things. We're validating, like we just spoken about. We're then syncing the data down. We're then automating these operations inside Revit and Navisworks, and we're picking up the metadata, any object-based selection stuff that we're doing, and one of the really important reasons for doing something like this is it gives us the ability to really massively optimize everything without compromising accuracy, fidelity, or any of the data. And the other critical requirement is that all of this stuff needs to be updated regularly. So whether that's monthly, weekly, whatever the case may be, this automated pipeline really deals with a lot of that. So in our eyes, at least 80% of a import pipeline on projects like these has to be automated. Because in all honesty, if it wasn't, humans are just going to fuck it up, and robots will obey. So in this export pipeline, we're also tagging everything. We're tagging everything with anything that we think might be useful, whether it's Revit categories, materials, levels, asset IDs, et cetera. And we're doing this in our exporter because generally both Revit and Navis are pretty slow to process this sort of information. And we split it off on the import side because Unreal could just handle it faster. And with this export pipeline and this asset tagging, we've really been able to reduce total average file size for everything, about 35% over native Datasmith. And again, the types of tags we are applying are, what is it? Where does it need to go? And why? And really maintaining that semantic structure throughout the export process so we can handle things later. So one of the things the importer does that's absolutely critical is turns nanite on everything. Nanite has to be used judiciously. Anything that has a shadow on it needs to be nanite. But one of the things that our pipeline does is breaks out anything with translucent materials, separates that as a separate thing, and makes sure everything that has a shadow has nanite. The other thing that we're doing, we're also streaming in a lot of data, and while streaming is not perfect yet, it does give us a lot of out-of-the-box performance gains. Even in older workflows like foliage painting, it really lets you, in a parallel way and in a non-partitioned way, lets you bring some of this information in a way more optimized way. And assuming you caught the preview of 5.6, they really turn this up to 11 with all new streaming optimizations. Combine that with stuff like PCG and HLODs, you start to stack performance gains, and then things start to really speed up. And the other really cool thing too is this is not just in runtime, but also in editor. So for a scene like this, which normally you could never have enough RAM to open, we've been able to get it down to the main level opening in editor in seconds, and that allows our devs to work quickly. So generally, our streaming philosophy is we think in layers of importance, and that streaming philosophy then drives the data pipeline. So we generally start with performance first, but the flexibility and the purity of the data really takes a second seat at this scale. So we think large, what we generally call surfaces and structure, large unique meshes that really define the overall shape of something and what you see from far away. Then a medium level that what we would call details. And these are smaller, mostly unique objects, mostly unique meshes, but they're things that can be instanced. Doors, windows are good examples of things like that. Roof parapets are good examples of things like that. And they often look very repeated, but they're usually not instanced. And so we have to plan for that. And sometimes, having limited instancing in the data, whether it was imported or not imported from the CAD, we can handle that with streaming. And then there's small things. So generally what we would call props, and this could be small, usually very small objects, but sometimes they can be visually pretty large. But most important, they are very much not easily instanceable. And if these things that are far away are a little bit less important to see than some of the bigger surfaces. So streaming large assets. So what I had mentioned, what we called surfaces are large, unique meshes, and how we chunk that up and tag it for streaming. One of the other things that is just a byproduct of CAD. Lots of architecture doesn't have much room for optimization. Walls are cubes, basically. And there's not much polygon reduction you can actually do to that. But we can still handle that with some intelligent streaming strategies. But you can still have lots of low poly objects, but lots of them, millions of them. And so what this allows us to do is really control that visibility effectively across the whole project. So generally, by the time we're done with it, our result is almost 100 times fewer meshes, no empty actors. Empty actors can really mess up streaming if you were to wear in other world partition systems. And it's also really important that all of the metadata is then transferred to the tags to these new mesh actors. So another streaming strategy we use is HLODs. And HLODs are a really quick way to generate and allow distant objects to still remain visible. Another thing to touch on and why instancing fails for a lot of things is there may be a lot of very, very similar objects, but they've got like custom rotations on them and custom attributes to them that they just can't be instanced. And if there's no HLOD generated for some of this stuff, it just streams in and out, fairly close to the viewer. And then, usually these assets are the heaviest of the CAD data. We're talking millions of mullions everywhere, and there's very little of them off screen typically. So we are also now working on some heuristics to identify all these unique meshes and allow them to be instanced rather than streamed. And then we're bringing in PCG, and this is where I think things get pretty interesting. Originally or historically, we would have been streaming all of this stuff in, but unfortunately, the levels are huge just due to object count alone and how many objects are in the outliner, and that's when performance tends to tank. But this was still when projects get to this sort of scale, things get really slow, and the meshes would really lag behind the viewer. Fortunately, 5.5 we're able to turn on some of this in PCG, and it's a really straightforward way of converting all this stuff into PCG assets, so that we can easily control the generation of them based on distance, dimension, tags, et cetera. And we can also then apply randomizations and reproject to the surfaces. So materials can be unique and UV'd or apparently UV'd, even if it wasn't UV'd. and also replace meshes too. So sometimes, for example, you'll have in BIM would be considered a pretty high detailed object like a pot or a sconce. For this type of is not detailed enough. And if you can't handle that in materials alone, we're able to now replace that. And it also gives us instant feedback in the editor, which means it's all then easily modifiable. So the other thing that we're doing, we are now converting everything to PCG, and that really has lowered our overhead. And yeah, when the meshes can't be directly interacted with, they are part of that PCG grid. And here's a quick example of a typical PCG setup. This one's pretty straightforward. We're grabbing an array of PCG data assets, and then we're generating all of that from the Datasmith imported data. And these points are all then filtered out, assigned by size in the grid. Larger details like props and trees, they can be loaded from far away. And the smaller stuff, we can be called more aggressively. And so this sorts through everything, and we can then place all of this entirely dynamically. And really the best part of it is Unreal manages all of this in real time, which is just amazing. So some of these examples of details and props that are all getting generated by PCG. Even structure and architecture we're generating with PCG. And here's some of the distance-based culling, which is just fantastic, which we can now do even if it's not in an HLOD. And then it's gone. So now that we've got all of this information in, we've got it all tagged appropriately, we've got all the data that we need in the BIM model to do something with it. We now then have to we have to connect it to data. And to do this, we're typically merging multiple data sources, whether it's Primavera scheduling data. Unfortunately, a lot of clients are still doing things in Excel, even with the biggest enterprises, all using SAP and Oracle systems. There's always an Excel sheet that sneaks its way in there somewhere, and we have to plan for that one, as well as SQL databases, MySQL databases, and we kind of have to consolidate all of that into one thing to then drive animation and visibility, and even we're using that to feed into our model filtering. So general basic pipeline here, we're bringing in file-based things together, connecting that in an API connector array, essentially, converting that into a new SQL database. We're then taking object storage for things like images and media and whatnot, and then bringing that through our API into Unreal. And what this really allows us to do is really have massive amounts of optimization without compromising the accuracy that we're doing. Then one of the other things that we're doing, we're bringing that into a native Unreal data table, and we're doing this for speed, really. Those data tables work really well with blueprints, and generally operate just a little bit faster. So then it comes to doing stuff with all these models and this data and manipulating the BIM. one example of that we're doing in the project that I'm about to show you is we are visualizing construction phases, and to do that we're mapping Navis task IDs to all the tag meshes, which gives us the ability to, with a really simple slider, scrub through and see where things are, which then allows the team to then catch coordination issues and do that at a really high level. So a pretty simple example on how to gather and then organize that model data. Data tables are great. They're super easy to integrate into blueprints. In this case, we're building an array of actors to then control that visibility, which another reason for really aggressively trying to reduce the actor count is making this sort of stuff more performant at runtime. And in this project, with millions of objects, it's like entirely hitch-free. So doing all these for loops over things, you would think, hey, if we're going to have to turn a million things on, be prepared to wait, and that's just not the case now. And this has been it's worked out quite well. And then the other thing that we can do once we've really come up with a really intelligent way of tagging everything, we can then find all the actors with those tags, and we can then dive deeper. We can see what's conforming, what's not conforming, and we can simplify the structure into something that can be manipulated with an integer. Whereas in typical construction scheduling software like Synchro or whatnot, you're dealing with a lot of different data types and things, and trying to manipulate the models like that. By converting everything to tags, we can then reauthor how those tags actually interact with the models. So like in this case, a really simple integer to grab a time slider and turn off millions of objects on and off. These are just some images, but I'll show it to you running here in a second. And even spawning new things like vehicles and things like that. While that plays, I'll grab some water. As you can see, this is video, and it's all turning on as fast as I was flipping through those slides. And in just those couple buildings alone, that was probably a couple 100,000 objects individually. So how to render 2 million objects without actually rendering 2 million objects? Some ways that we're doing this, now that we have this really defined system with tags, we can then apply rules to this, what to include and what not to include. So that hierarchical tagging and visibility logic, we can then say, okay, if something is behind something else, we can turn it off if we don't need to. So the method we tend to take is be really smart about how we're streaming it rather than brute forcing it. And like I was talking about earlier, we're using that view-based culling and tag filtering to then adapt and thin the scene out. Been talking all about BIM models and BIM data, but what about non-model based stuff? What's really cool is we can then also use that same system of tags in other things, media assets, UI elements and components, videos, etc. So here's an example of a pretty straightforward blueprint to sort through all those non-geometry assets using the same tags that the geometry is using. So that, for example, we can come in, we know what district we're in, we know what projects we're looking at, and we can sort and filter a gallery based off all those same tags. Yeah, as well as pull in any other information or images that may be related, such as their marketing CGIs and stuff like that. And that also works with UI elements and generated non-model things. So in this case, generating splines and coloring things, coloring objects by tag, but we can also then filter in and show detailed information in the user interface on a per project level, on a per object level, whatever it might be. We can all access it through that tagging system. And again, doesn't matter the size or the scale of the project because it's now operating so efficiently. We can generate all of this at runtime without a second thought. And in this case, all of this data is getting updated on a quarterly basis. Literally every model in here changes on a quarterly basis, and it's still just running smooth as can be. So to wrap things up, really, performance and philosophy really drive the pipeline design. And planning that out in the beginning is critical. You need to know what you're going to be doing to design something that's going to work well. And in this case, we had to start with performance first because just the pure density of this project. But in this case, flexibility and the purity of the data take a second seat at this scale. And I know I mentioned it earlier, but it is absolutely critical to work directly with the client to define all of those goals, but then also to define and validate the BIM data, which in this case has been a huge win for us, but also for them. And historically, we had used or we would use Viz to help designers and architects visualize their designs. But now we're doing that at the scale of an entire city scale project, and all the project data that we need to really achieve this and that our clients demand is there now. And this, of course, wouldn't be possible without Unreal's open world game systems, which are just increasingly becoming more and more performant with every engine release and more robust for all of the users. Things like data layers and streaming grids and runtime generators and HLODs are all built in. They do require a good amount of learning and experimenting to figure out, but with the right recipe, you can get that figured out and apply it to your work. And UE now also has a lot of capability to optimize content as it's imported, and we do a lot of this. Everything from merging meshes, setting materials, setting nanite, and this is all happening on the way in, informed by the way out from Navis. And this is even enabled giving feedback to the Revit operators to how to build their models better, and everything then really comes together in the end. And of course, I'm up here showing this stuff off and talking about it, but yeah, we've got an amazing team. So thanks to the team. Some of you guys are here. And, yeah. And thanks to everybody for showing up and listening to us talk about BIM. It's been a really interesting and fascinating project to work on, and all the hard work and all the thinking has really paid off in dividends for the project. It's enabled so much for the client, and we're just showing one little part of it today. So thank you, everybody.